Okay, so first we're going to talk about inverse circular functions. Well, actually, first we're going to talk about inverse functions, and then we're going to relate that to inverse circular or trigonometric functions. So if a function, if f is a function, then if function f is blank, then f has an inverse function, f inverse. So if a function f is 1-to-1, and we're going to talk about what that means. We've talked about it already in section 4.1, but we're going to review it right here. Then f has an inverse, f inverse. A function, so the definition of function means that it's going to pass the vertical line test. What that means is for every x, there is no more than one y. All right, if you think about that, for every x, so here's the xy axis. So now pick an x value. For every x, you cannot hit it more than one time. If you hit it twice, that fails the vertical line test, and so it is not a function. Okay, so then if you just invert that, okay, or interchange that, I suppose, then 1-to-1 must be the horizontal line test. Or for every y, there is no more than one x. So there doesn't have to be an x value to give you every y value, but if there is one, there aren't two. Okay, so usually we say things with the x input. Hang on, for every y there is no more than one x. Usually we say things with x instead of for every y. We would say something about for every x. So we could say there are no two x's that give the same y would be another way to say it. Okay. All right, the domain of f is the range, because we interchange x's and y's, the range of f inverse, and the range of f is the domain of f inverse. The graphs of f and f inverse are reflections across the line y equals x. Because you are interchanging them, then that makes sense. This is where they would touch each other. Like thinking about looking across a mirror and your fingers touching the mirror, this is the place where the mirror would be. This is where they're interchanging, but they're equal here. Okay, so to find f inverse from f of x, first you replace f of x with y. That's just the definition of f of x. Then you are going to interchange x's and y's. That's the definition of inverse. Then you are going to solve for the new x. This is so we can get the new equation of the function. Solve for the new, not new x, new y, sorry. And then finally you replace y with f inverse of x. And this is so we can tell them apart, because if you just left them both as y's, you wouldn't know which one was, I mean, they're inverses of one another. But this is so I can find the inverse function. All right, in the remainder of this section, we'll use these facts to develop the inverse circular or trigonometric functions. So first we're going to start with graphing y equals the sine of x. So y equals the sine of x has 4 parts to it. Okay. I mean, there are infinite number of parts, but we're just going to do 4 on the right and 4 on the left, just to get a basic idea of it. All right, and then it goes up to 1 and down to -1. And it goes middle up, middle down, middle. And then we connect it in a nice curve, and that is 1 period of the sine function. And then I'm going to go to the left also and graph more. Not that I need to, because we can already see that it fails the horizontal line test just from 1 period of it. But we're going to graph it because it's going to be important for our domain later and our range later. Okay, so is the sine function 1-to-1? Why or why not? Well, if you notice, I mean, if you draw a horizontal line through it, it fails multiple times. In fact, it fails an infinite number of times because sine keeps going in both directions forever. So, no. Now, it says why or why not, so I need to give a specific reason. So that would be giving me 2 different x values that give the same y value. So I'm just going to do like a pi over 2 equals, all right, and then another place where it is equal to 1, not here, not negative pi over 2, but at 1 pi over 2, 2 pi over 2, 3 pi over 2, so negative 3 pi over 2. So that fails the horizontal line test because there are 2 x's that give the same y. Okay. All right, there are many domains to which we could restrict the sine function in order to force 1-to-1ness. However, it is convenient to restrict y equals sine of x to a domain of, all right, so what is convenient? I mean, what it's saying is we want to restrict it so that we do pass the horizontal line test. And there are many places, like I could do it from here to here. See, that little s right there doesn't fail the horizontal line test. Or I could just do from like here to here, okay? But I want to get the entire range in, as much of the y values as I can. And I also want to try to cross my y-axis so that I get negative x values and positive x values, and get negative y values and positive y values. So if you just stick close to the y-axis and draw your box out as far as you possibly can. Now, if I go past 1, it starts coming back down, so I'm going to fail the horizontal line test after that. I mean, not 1. If you go past pi over 2. Okay, and then here again. So I'm going to restrict the domain to be from negative pi over 2 to pi over 2. All right, and then the range is still, I got the full range into it, so the range is from negative 1 to 1. All right, the inverse sine function is written y equals, now on your calculator it looks like this. That does not mean flip it, okay? It has a different input than the sine function, so you can't just flip it. It has a different output than the sine function, which means you can't just flip it. All right, and then we get another way to write it so that we're not confused and think that that's an exponent, which it is not. Then we write it like this. And remember, these x's are actually the y values on our unit circle. All right, so the inverse sine function has a domain of, well, it comes from this range. So it has a domain of negative 1 to 1. And it has a range of negative pi over 2 to pi over 2. Okay, so what this means is that we can think about, I want you to think about the y equals sine of x. And think about its input. So I'm going to actually write it as y equals sine of theta. Okay? Its input is an angle, right? We rotate around the unit circle a lot of times. I mean, you don't have to, but any angle can go in. And its output is a ratio of the sides of a right triangle. All right, well then that means for y equals, actually not y equals, we're going to write it like this. So now we're going to interchange the input and output, so that's theta, and then it would be the sine inverse of y, or arc sine. Remember, you can write it either way. So its input is a ratio of the sides of a right triangle, and its output is an angle. Okay? All right, so we can think of y equals arc sine or y equals sine inverse of x as what y in the interval negative pi over 2 to pi over 2 makes sine equal x. And we'll get into that in a minute when we do some more examples, but let's graph it using that idea, okay? So first of all, the range is still negative pi over 2 to pi over 2. Just recapping that. I know I've said it a lot, but it's good for you to get that in your head. And the domain is negative 1 to 1. So notice these don't even look like angle values, right? Okay, so if my domain is negative 1 to 1, then that's going to be here and here. And then if the range is negative pi over 2 to pi over 2, then that's going to be here. All right, and I mean, these are totally different scaling, right? This is a one scale of 1. These are scales of pi over 2. Okay, and then I'm going to graph my sine function. So let's think about what this is. So when you take the sine function, then you interchange its x's and y's. Well, 0, 0, when you interchange it, is still just going to be 0, 0. So I'm just going to put that there. Okay. All right, and then the point negative pi over 2, negative 1 is now going to be negative 1, negative pi over 2. So there. And then likewise, the other one is going to be 1 pi over 2. All right, and then from 0 to negative 1, it kind of cups upward, right? It's concave up. So from 0 to negative 1, this one is going to be concave down. And then the other one goes like that. And that's it. You cannot draw arrows on these. They just stop right there and right there, and that's as far as you can go. All right. Now, you don't really need the graph of arc sine to be able to answer these questions. You just still need your unit circle. So when I see the word arc, or I see the inverse, okay, I'm going to think, where is, okay? That's what I think in my head when I see it, okay? So y equals, remember, this is actually a theta, okay, because the output of an arc function or an inverse function is an angle. The input is the ratio. So I'm just going to go, where is sine a half? All right. Now it's important to think about the range where you're allowed to answer. All right. You can go from here to pi over 2, or from here to negative pi over 2. That's the rule for the range, right? It's from negative pi over 2 to pi over 2, which means it's important to think about on your unit circle, you're here rotating down or here rotating up. So where is sine try that again. Where is sine of theta equal to 1/2 within the restricted domain of sine, or in other words, the restricted range of arc sine. Okay, so where is sine 1/2? Well, that would be the shorter one, the one closer to the x-axis. So that is going to be pi over 6. Okay. For the next one, let's rewrite this as y equals the arc sine, just because I don't like to write the sine -1, even though that is what it is on your calculator, is the sine with the -1, which still means arc sine, or sine inverse. Okay, so where is sine -1? Again, you can only answer from 0 to pi over 2, or from 0 to negative pi over 2. So where is sine -1 on the unit circle? Right here, which is negative pi over 2. Okay? Finally, where is sine -2? Where is sine -2? Well, if you think about the unit circle, it only goes down to -1 or up to +1. And we learned this a while back, opposite over hypotenuse, it can never be bigger than 1 because the opposite side, by definition of a right triangle, or the definition of the hypotenuse, is the opposite side is always smaller than the hypotenuse. About opposite over hypotenuse. The hypotenuse is always bigger, so this is always going to be a proper fraction, which means it can never get bigger than 1, or its magnitude can never be larger than the magnitude of 1. So it can never be on the other side of -1 either. So this does not exist. And if you just think about your unit circle, you know this also, because the radius of a unit circle is 1. So that's as big as your y value can get. Okay, let's move on to the cosine function. So we're just going to quickly go through this. This is 2 pi, because it works in pretty much the same way. All right, and then this is 1, and this is -1, and then it goes up, middle, down, middle, up. Remember, these kind of curve downward. It's not my best drawing of cosine yet, but that's alright. Okay. Alright, now, if you look at this one, you can see if I try to stretch it around the y-axis the same way I did sine, it fails the horizontal line test. So the cosine function can't be, you can't have negative inputs, because the moment you go left, you get, to restrict them. To restrict the cosine function, you can't have negative inputs, because the moment you go left, you start failing the horizontal line test. So the best we can do is be on the y-axis and then go right. So keep going, keep going, keep going. Now, if I go beyond this point right here, I again start failing the horizontal line test. So the domain, my restricted domain, is going to be from 0 to, now that's pi over 2, so that's pi, which means that's going to be the range of the inverse one. Okay? And then my domain, my range of my cosine function, restricted or not, is still -1 to 1. So I still managed to get all the possible y values out, which means that the domain of this one is still going to be -1 to 1. All right, so -1 to 1, and then 0 to pi. So this is pi here, which means this is going to be pi over 2. Okay. All right, and then I'm going to graph it. So 0, 1 is now going to be 1, 0. Pi over 2 is 0, so 0 pi over 2. And then pi is -1, so -1 pi. Okay, and then it's down and then up. Remember, I started here, so this is going to be up and then down. Oh, that got really fat. It's holding it. Up and then down. Oh, I know why. My pen is... I didn't choose the smaller one. That would be why. Okay, one more time. Up and then down. That kind of looks like it's failing the vertical line test there. It's not supposed to. It's just there. Okay, so again, you don't need to be able to recall this graph in your head to be able to answer these questions, because you already have the unit circle memorized. So you can just use it again to answer these. So we think, again, when you see arc, where is cosine 1? Now, make sure you pay attention to the restricted domain of cosine, or the restricted range of inverse cosine. Okay? So you can only answer from 0 to pi, which means only positive angles for this guy. All right? From 0 to pi. All right, so where is cosine 1? Well, that'll be right there at 0. All right, now this one is where is cosine. So arc cosine is a little funnier to write because it's got the 2 C's. -√2 over 2. Where is cosine -√2 over 2? But again, only between 0 and pi. So where is cosine even negative in this place? Well, that'd be right over here, and the root 2 over 2's are recognizable as the pi over 4's. So that's 1 pi over 4, 2 pi over 4, 3 pi over 4. Okay, so next we're going to graph the inverse tangent function, and we're just going to quickly go through this with our knowledge of the tangent function as well, just like we did the cosine one. Now, if you remember, the tangent actually has vertical asymptotes because it's sine over cosine, and so cosine can't be 0, and cosine is 0 at the y-axis on the unit circle, or in other words, pi over 2 and negative pi over 2. Alright, and we found these earlier. So this is, if that's pi over 2, this is pi over 4, and there's 0. So the tangent of 0 is 0, and then pi over 4 is 1, or negative pi over 4 is negative 1, because tangent is negative in quadrant 4. Okay, and then we just kind of curve it up, and we never cross that vertical asymptote, and then we curve it down. So it kind of reminds us of the cubic, but it's not. I mean, these are pi's, and these are radians, pi over 2, pi over 4, so on and so forth. And these are outputs, which are the ratio of the sides of a right triangle. Okay, so, and remember, it does repeat again and again for all the odd pi over 2's. We talked about that also, but we're not going to consider it, because if we repeated it, it would fail the vertical line test anyway. So we're restricting it so that we can, so it would fail the horizontal line test, not the vertical one. It would fail the horizontal line test if we did one over here and forever and ever. It would infinitely fail the horizontal line test. So we're just going to think about one period of the tangent function. So the domain, since you can't touch the vertical asymptotes, is negative pi over 2 to pi over 2. Alright, and the range is all real numbers. Alright, and then the asymptotes are x equals negative pi over 2 to pi over 2. And pi over 2. And I don't need to put their vertical asymptotes. We know that by the equation x equals. Alright, so now if we invert it or interchange the x's and the y's, then that means that these will now become y equals negative pi over 2 and pi over 2. Well, the line y equals a number means that it's a horizontal asymptote. And here's going to be pi over 4 right there, and there, and then this is pi over 2 going that way. Forever in both directions. It's a horizontal asymptote. Okay, so now we're just going to interchange the x's and y's. So 0, 0 is still 0, 0. And pi over 4, 1 is going to now be 1. So this is 1 and negative 1. So 1 pi over 4. And then likewise, negative pi over 4, negative 1 is going to be negative 1, negative pi over 4. Okay? So from 0 to 1, it curves up, so this one is going to curve downward, concave down, but approach that without ever touching it, and then upward and approach it but never touch it. Alright? So its domain is all real numbers because it goes on forever and ever, and then its range is negative pi over 2 to pi over 2, just like the range of, just like the domain of the tangent function. Okay. So this is basically a summary of what we have done. And notice that cotangent, secant, and cosecant, the arc functions of them, are on here as well. But I would highly recommend that you just remember these three. Okay, and then we're going to see down here how to change any of the reciprocal functions into the sine, cosine, and tangents, just like you know how to do them for the original trigonometric functions. The inverse ones are going to work in much the same manner. All right, so when you go to answer your questions, if it starts with an arc sign, if you go to think about them, if it starts with an arc sign, then what you're going to want to do is you're going to, or arctangent, notice their ranges are the same, except for these you can include it, these you cannot include it. So for sine and for arc sine and for arctangent, you're going to want to only answer from here to here. All right, so from 0 to pi over 2 or from 0 to negative pi over 2. That's where your answers can come out because it's the output of the arc. Okay, so that would be arc sine of x and for arc tangent of x. And include for arc sine and exclude the endpoints for arc tangent. All right, and then for arc cosine, you can only answer here, like we've already reviewed, but just reminding you. So y equals arc cosine of x, right? So now what about the other three? Well, since they're just reciprocals of the first three, then we can think about them by using the reciprocal identities. Well, first, I'm going to use the definition of inverse, which says that if y, or theta, is the arc secant of x, then the secant of theta is just x. In other words, I am taking the secant of both sides. And since these are inverses, then by definition of inverses, you just get x. And then on this side, there was nothing to do with it, so I just do that. Okay, now, what is the secant of y? Well, it's 1 over the cosine of y. So now just solve it again for y, and by cross multiplying here, or flipping both sides, either way you want to think about it. So cross multiplication, and then dividing by x, you get the cosine of y is 1 over x. And then I take the cosine inverse of both sides, and I get y equals the cosine inverse of 1 over x. So notice, with arc functions, you don't flip the whole thing. So the secant inverse of x is not 1 over the cosine inverse. Instead, it's just the cosine inverse of 1 over x. So you flip the inside, not the whole thing. Okay, or the argument. You flip the argument, not the answer. Okay, so find the exact degree measure of theta for each. All right, so tangent of arc tangent of 1. So where is tangent 1? So remember, with tangent, you can answer here to here, not including these. Okay, so where is tangent 1? Well, that's right here, which is at pi over 4. All right, where is secant 2? That's what this is. Theta equals arc secant of 2. That's where is secant 2. Or in other words, theta equals the arc cosine, because secant and cosine are reciprocals, and then you flip this 1/2. So where is arc cosine 1/2? Well, you can answer from here to here. And where is cosine 1/2? Well, that would be the one closer to the y-axis. So because it's 1, 2, 3, so 1/2 is right there. Or I could be over here, but that would give me cosine is negative over here. So it's going to be this one, which is pi over 3. Okay? So again, you don't need to memorize anything for the reciprocal functions because you already know how to do them. All right, and then with using the original functions. Okay, so now we want the arc cotangent of this. Well, that is the arc tangent of 1 over negative 0.3541. Okay, well, the arc tangent of that, I'm going to have to do that in my calculator because that is not anything nice on the unit circle. So I'm going to make sure I'm in radians, first of all, because all these other ones are in radians. So, I mean, I could answer it negative 90 degrees to positive 90 degrees. That's also allowed. All right, but I'm going to just be in radians because all the other ones were. So I'm assuming my answer needs to be in radians. So that's go to mode and check that you're in radians. Now, when you're doing arc stuff, you have to check your mode. You can't even override it with a degree symbol or anything. So I'm going to go to mode, and I'm going to check that I'm in radians, and I'm not. I'm in degrees, so now I'm going to turn it to radians, and then quit. That's second mode. All right, and then I'm going to hit the, so there's another reason to remember how to do, that you flip the inside instead of the outside, because there is no arc cotangent button on your calculator. You have to hit the tangent inverse, and then 1 over negative 0 point, or I could put a negative 1 there and positive 0.3541. Doesn't matter where to put the negative sign. So then tangent inverse of 1 over negative 0.3541. All right, and I get that it is approximately, and then I've got 4 decimal places here, so that's how many I keep here. Negative 1.2305. Or if you were doing significant figures, then negative 1.230 or 231. Okay, and those again are radians, so not degrees. Now I could answer that in degrees. So what I want you to do, I'm going to change my mode to degrees. So everybody change your mode to degrees with me. And then do second enter, which brings up the last thing you just did. Or in other words, just do this again. And then hit enter. And this is also, so another way I could write this, since it wasn't, oh, it says it's find the, oh, I didn't follow the instructions. None of these are right. I should have been in degrees. So let's go back and actually change these. So what? Pi over 4 is 45 degrees. I'm just not used to answering in degrees. I like for you guys to think in radians. So, all right, correct execution, wrong answer. So pi over 3 is 60 degrees. Okay, and so this one actually was in the wrong one. I need to be in degrees, which is negative 70.50. Let's see, I'm going to do 4 decimal places, so 0.9. And then don't forget your degree symbol. So radians do not need a symbol. You can write rad after it or radians after it if you would like, but they're not required. They have no units. But degrees do have a symbol. Then you must follow it. Okay. And then okay, so now it says find the exact degree measure. You can't find the exact degree measure for this one. These you can, because they're nice and on our unit circle. And I wouldn't do this to you on a test or anything. I would say if possible. Okay, so there should be exact if possible right there in parentheses to make sure that you understand that if it's not possible, it doesn't mean that it's not possible to get an answer. Exact is not possible. Okay. I mean, besides this would technically be the exact answer without, but it's not as useful as negative 70.5 degrees. So this is technically the exact one, but if I want an answer like a useful answer, then exact one's not possible. Okay? Alright, so maybe I should put not possible. Not useful is more like it. Okay. So I'm just going to erase the not possible. This one, let's change that in your notes, would be the approximate one. Okay, so next it says to find the approximate radian measure of theta for theta equals the cosecant inverse of negative 3. Alright, well it says radians this time, yay. So I'm going to go ahead and check my mode and change it to radians. Alright, and then quit. And it also says to find the approximate, so I know I'm going to be using my calculator, that's why I went ahead and changed my mode. Alright, and then I'm going to, my calculator does not have cosecant, so try it out, see what you think. That is going to be the sine inverse. And then I flip 3 and get third, well, negative a third. Okay, and that's possible because sine just has to be between -1 and 1. So arc sine input has to be between -1 and 1. And then I just do it in my calculator. So second sine, and then -1/3. And then I get approximately -0.3, -0.3, I guess. I just want one significant figure. Or you can do like 0.34 or whatever. So on the exam, it's generally 3 decimal places. So let's go to 3 decimal places. And we'll do the tenths, that's thousandths. So we'll just add that up there. Okay, so then that would be 0.34, and it's a 9, so that's why I got the 4. Alright, and that's radians. If you're not sure where that is, change it into degrees, but you should know where 0.34 radians is based on, you know, -pi/2 being 1.6 about. So it's very close to the x-axis. Alright, evaluate each expression without using a calculator. Alright, now we've done this before, but now we're just reminding you. For some reason, students forget how to do these a lot. So I want you to think about the input and output of tangent inverse functions, and that'll help you with what you're supposed to do with this. So the tangent inverse means that this output is an angle. All right. So if I think of that as the output is an angle, then I can say, well, let's just let theta equal be the output. Let it represent whatever the tangent inverse of 3/2 is. Well, then by definition of inverse, then that must mean that the tangent of theta is 3/2. Okay, so now it originated from an inverse tangent, so I know that it's either going to be up here or down here. Well, since it's positive, it's going to be up here. So I'm going to draw my right triangle up here. And then tangent is opposite over adjacent. So then 2 squared plus 3 squared equals c squared. So then that's 9, 10, 11, 12, 13. So that's root 13. All right, well, if tangent is theta, then now this equation, or this expression, just becomes the sine of theta. Well, I just drew out theta right over here as a ratio of the right triangle, a ratio of the sides of the right triangle based on my tangent information. So now sine is just opposite over hypotenuse, so 3 over root 13. Or, in other words, 3 root 13 over 13. No, you don't have to rationalize, but you know, I can't help it. So, there it is. Okay, so now let's try this one. I recommend that you try it now and see if you get it right. See if you can do it along with me or faster than me. So I'm not going to talk during this one. I'm just going to write it out so that you can just look down and try it out and look up when you need to. Okay. All right. Now we have to evaluate each expression without using a calculator. But I've got some addition here, and I've got a 2 there. And remember, you cannot distribute a cosine. That is not allowed. There is no distributive property for trigonometric functions. And you can't just double the answers. You can't just pull the 2 out here. All right, you must use identities. So how do you add two things? All right, well, this one, I mean, it's the same idea. I'm just going to let, what? So we're going to say, let A equal arctangent of root 3 and B equal arcsine of 1/3. Then that means that the tangent of A equals root 3, which now I can draw that. Whereas tangent root 3, that would be quadrant 1. So here's A, opposite over adjacent. All right. So then that's C equals the square root of A squared plus B squared. So 3 plus 1, which is root 4, which is 2. All right. And then let's do it for B. So the sine of B is 1/3. And where is sine positive and allowed to come out for the arc? Also in quadrant 1. These do not both have to be in the same quadrants. Notice this is actually on the unit circle. This one's not. That's fine. Okay. So then now let's see. Opposite over hypotenuse is 1 and a 3. So then A squared plus B squared. So then B is the square root of 9 minus 1. So root 8. Which is 4 times 2, so 2 root 2. Okay. All right, so now this bypasses all of this and just becomes the cosine of A plus B. Well, A is that. I mean, we're going to use this triangle, and B is we're going to use this triangle. I should have labeled that. Let's put a B in there. Okay, so now I just use my sum and difference formulas. So cosine quadrate, so that's cosine A, cosine B, minus sine A, sine B. Which is, all right, cosine of A is adjacent over hypotenuse, so 1/2. And then cosine B is 2 root 2 over 3. Minus sine of A is opposite over hypotenuse. And sine of B is opposite over hypotenuse. So then finally I get, well, these are going to cancel there because it's multiplication. Nothing cancels there. Oh, you know, though, I don't want to cancel those because I'm just going to have to get a common denominator anyway, and these already have that happening with this being root 6. So that's, try that again. Okay, so that is 2 root 2 minus root 3 all over 6. Okay. This one works in much the same way. It's just, I'm going to change my color so we don't get them mixed up here. This is just letting theta or A or B or whatever you want to let it be, letting it equal arcsine of 2/5. So theta equals arcsine of 2/5. Well then, so that would be that the sine of theta is 2/5. So now I'm going to put that. That's quadrant 1. opposite over hypotenuse. So then b is the square root of 25 minus 4, which is root 21, which is 7 and 3, so not simplified. So that's root 21. All right, so then now this becomes the tangent of 2 theta. All right, so now you have to think of your double angle formulas. Let me label this as a theta. It's good to keep my triangles labeled, even though there's only one triangle in this one. This one's especially important to keep them labeled. This one there is only one, so I'm probably not going to get confused. All right, so now I just need the tangent of 2 theta. Well, I don't know if you remember it from the last section, but it's the sine of 2 theta over the cosine of 2 theta, or it's what, 1 minus sine theta, I mean, not sine, 1 minus tangent squared theta. Okay, obviously I don't remember it either, so let's go back and look. I would do the sine of 2 theta over the cosine of 2 theta. But like I've told you, most of my students really would rather just memorize them. They say it's easier than having to do all of that. So those are the half ones. We're almost there. The double angle. There we are. There it is. 2 tangent, wow, I was way wrong, huh? 2 tangent theta over 1 minus tangent squared theta. So 2 tangents, 1 minus tangent squared. All right. So 2 tangent. So it's 2. That's 2 tangent theta over 1 minus tangent theta. Okay, like I said, I would have just done sine of 2 theta over cosine of 2 theta, and then that would be 2 sine theta cosine theta over whichever one of the cosines you want. Cosine squared theta minus sine squared theta. And then I would fill these in using my my triangle. But if you have this memorized, then this one probably is a little bit faster. So, all right, 2 tangent theta is opposite over adjacent. So the tangent of theta, I'm going to write that over here so I can go ahead and rationalize it. So the tangent of theta is opposite over adjacent, so that's 2 over root 21, which is 2 root 21 over 21. Okay, so then 2, and then 2 root 21 over 21. All right, and then 1 minus 2 root 21 over 21. Sometimes it's not best to rationalize first. It's just best to stick it in there first. This one, no, I don't think it matters. 6 to 1, half dozen the other. Okay, so now I get 4 root 21 over 21. Okay. Over, and then I got to get a common denominator, so 21 minus 2 root 21 over 21. Okay, and then now it's nice because those will cancel when you flip and multiply them. So you get 4 root 21 over, be careful when you cancel denominators, like make sure it's really the denominator of the numerator and the denominator of the denominator that cancel. Otherwise, just go ahead and flip and multiply them and make sure you're right. And then that's 21 minus 2 root 21. And it may be tempting to cancel those, but don't do it. Don't be tempted. Because you can't split up a numerator to 2 separate denominators, so it's just stuck like that. Right? This has subtraction here, so this root 21 is not a factor of the entire denominator, and only factors cancel with division. Okay, So that's the answer for that one. And we don't need to rationalize. I told you don't have to do that anymore for me. Alright. Oh, I must have made a new page so that it would fit. Okay. So now we're going to do it again with sine of tangent inverse of u. Now, I don't know if u is positive or negative, so I'm not sure which quadrant to draw it in. So we're going to do two scenarios. We're going to say, let u be positive, and we're going to try u being negative. Those are my only two possibilities for u, so I should be able to do it either way. Alright, so let theta equal the tangent inverse of u. Alright. Then that means the tangent of theta equals u. And now I can draw this in my... now, u is positive for this scenario and negative for this one. So for u being positive, that would be here. Alright, opposite over adjacent, so u over 1, and then I need to find out what c is. So c is the square root of a squared plus b squared, so 1 plus u squared. Okay. So I'm going to write that on there. I mean, this is the exact same thing we've been going through, it's just got u's instead of numbers. Alright, and this is theta. This is my representative triangle for theta. Alright, now I'm going to find out. So now this equation just becomes, this expression, sorry, just becomes the sine of theta. Well, that's opposite over hypotenuse. So that's u over the square root of 1. And I was going to put u squared plus 1, but seeing as I wrote it as 1 plus u squared, I'll do it that way. Okay. Over 1 plus u squared. And you could rationalize this as this would be u root 1 plus u squared all over 1 plus u squared. But this is completely fine. Okay, now if u is negative, let's do that one. Well, that would be here or here. Arc tangent is only allowed in quadrants 1 and 4. So there it is. And again, we're just letting theta equal the arc tangent of u. So then that would mean that the tangent of theta equals u. Alright, so opposite over adjacent. You don't write a negative u is negative. So if it's negative 2, for instance, and you wrote negative u, that would be negative 2, which would be incorrect. So we're just saying u is already a negative number, so it's correctly defined right there. Okay. Well, this is the same as this triangle, it's just flipped, right? So I don't need to find c again. I can just go ahead and label it as the square root of 1 plus u squared. Okay? So then, if this is, no, it's not theta, sorry, it doesn't go that way, because we started with an arc, so it actually goes that way. That's theta. Alright, so then now my expression is just the sine of theta again. Well, the sine of theta is opposite over hypotenuse, so again, it comes out to be this. So you can see, it doesn't matter if it's positive or negative, because it is already taken care of with the negative in the variable, alright, then the sign, it will come out appropriately depending on the actual sign, positive or negative sign, of u. So if u is positive, then the sine of theta will come out positive, as it should in quadrant 1. And if u is negative, because this is squaring and all that anyway, then it will still come out, negative, just as the sine of theta should in quadrant 4. Okay, so now let's try, so now that we've learned that, you don't have to draw it in both quadrants. You can just do it in quadrant 1 if you want, but I do like the idea of thinking about it and making sure that you understand why it works out, even if you don't consider the negative. Okay, so for this one, we're going to let theta equal the sine inverse of u. So then the sine of theta equals u. And then we're going to draw this. Now, this one actually can only be here because I can't do, or no, it could be here or here again. Sorry. And then, let's see, this is theta. All right. And then, let's see. So that's opposite over hypotenuse. And then now, so that's b is the square root of 1 squared, so 1 minus u squared. Take a minute if you need to and figure that out on your own. So that's 1 minus u squared. Okay, so then this now becomes the cosine of 2 theta. So that we need an identity, right? You can't just do the cosine of theta and double it. Remember, anything funky in the middle here has to use a trigonometric identity. So this is cosine squared theta. This is the one I know, so this is the one I'm using. Minus sine squared theta. You could use any of them. You could use the 2 cosine squared minus 1 or 1 minus 2 sine squared. So I do know 3 of them. This one's just the one that I use the most. So cosine is adjacent over hypotenuse. So that's going to be the square root of 1 minus u squared over 1 squared minus, and then this one here is going to be the sine, so opposite over hypotenuse. So u over 1 squared. So I get 1 minus u squared, because the squared and square root cancel over 1, but that's fine, minus u squared. So I get 1 minus 2 u squared. And there you have it. And that's all I'm going to make today. Okay. Okay. So that's the end of that section. I highly recommend that you do some homework or make sure you ask me any questions if you have them.